Okay, we're getting started. All right, this is a great picture. We love this picture. Oh, yeah, and actually, I want to show something. First of all, let me like this. Actually, you know what? I'm gonna stop sharing for a second so that you can see. Stop the share. So. Oh,
Whoa.
oh, I see. You gotta go like
You're
this.
racing yourself.
So this picture, what does this picture show? Somebody tell me.
The table, the page table.
Page table, which is the page table? The thing that's called page table. What do we use why do we use the page table for?
So remember where we
Or each process starts their things in memory.
Where each process's pages of memory are actually located, because he thinks it's located at PD, but it's really at FD. And we need to get that F. The F is stored in this D. And that's in this page table. And so we use the P as an index into the page table, which tells us one very important thing. The page table needs to be contiguous in order for this to work. Contiguous, 48 contiguous states. It needs to be in a row, because if P is our index into it, then if P is like 10 million, then we need to go to row 10 million. It needs to all be in one spot. So even though we've succeeded in dividing up the memory into pages, we have an exception, a big exception, which is the page tables itself. All the page tables for all the processes have to be contiguous. So we didn't really solve our problem 100%, because we have these large page tables. Well, if they're not too large, it's not such a big problem. But if they're quite large, then we're going to have that same problem of contiguous allocation. That's one thing I want to say. The other thing is, what is this TLB? Remember what the TLB is? The TLB says, well, a reading from the page table, which is in RAM, is going to be slow. Let's put it in cache. So we make a TLB, which is our cache. And that means that some of these lines will be in here. Anytime we find a page, a new page, we'll shove it in here. And when this is full and we didn't find it over here, we'll have to grab it from here and then change our TLB to reflect that new page that we found. Now you may ask yourself, well, guys, I'm going fast, so there's no time to talk to each other. You may ask yourself, wait a second, didn't we in computer architecture, didn't we learn also about caching? What was that all about? Didn't we have caching over there? How does that fit with this? So what that was like this. We ignored this whole concept of pages, and we just said, imagine I'm the only person and I just develop an address like this, PD, and I want to find it in memory. And that, we said, could be slow. So we said, let's put a cache. So we made a cache over here. And this was our cache. And we said like this, if we want a page PD, let's say, 111,000. So we look, if it's in our cache, then we see 111 over here, then we get it at 111,000, we get the data. If not, we go to the actual memory, and then we change the cache. So the cache is actually a copy of this. So we have, for example, this is our computer memory, and some of it, this is our program memory. Some of it, this part, let's say, we put in cache. So all that's happened, so how do we put those two together? We put those two together when we finally, now we're adding this other part. When we finally generated the real address, which is the FD, we're not going to go straight to memory. We're actually going to go to this cache that we learned in computer architecture. That's still there. We're just not talking about it in this course. But I just wanted to clarify, in case you get confused, isn't this a repetition of what we did before? No, it's the same principles as we did before, but it's a different application of them. We're using it now on a different level, on generating the FD from a PD. Before we didn't talk about an FD, but now when we finally have the actual physical memory, we're going to go to the cache and look for it there. And if not, then we'll go to the actual memory.
What does the TLB do?
The TLB is just for the page table. What's in the TLB is page table entries or rows. Entries. Page table entries, which are not memory. What's in the cache are memory entries or memory entries, let's say. Memory data. Now, actual data is in the cache. This is not actual data. This is completely irrelevant to us. This is not the data we're interested in. We're interested in this data or this data. In the end, we want to do a read. We want to read a byte or a word. It's this this is just to get us to the right place. This is just mapping. This is like, if you think about it, imagine before there was Waze, people used to actually sell, people should actually have in their trunk, like, you know, all 50 states, maps for every state, Florida, California, what? All contiguous states, unless they were planning on driving to Alaska. But they had all the states in their glove, in their trunk. And therefore, when they got to the new state, they would have the map. But let's say they were planning to drive from New York to Florida, they knew they're gonna hit Virginia and South Carolina, North Carolina. So those 6 of them, they put in their glove compartment. And that's their cache. So that's the TLB, but that's just the mapping. In the end, they still want to get to grandma's house, and the actual memory is not in the TLB. Okay, so that's just a completion. So what are the 2 points that I said just now? Somebody repeat maybe the 2 points that I just said about this picture?
Grandma's house.
What?
That we have the table with all the page entries so that we can know where to map to.
Yeah,
And then once we know where to map to, we have another cache that could actually store where we're mapping to.
right.
instead of
That's the second point I made. What was the first point I made way back?
About what?
All the information is irrelevant except for what we need.
That's not the real.
It's all
Is
contiguous.
that this has to be contiguous. That this has to be contiguous. And that's the problem, yeah.
What is the page table like physically? Is it
Physically RAM. It's RAM. It's RAM that's been allocated to the operating system.
got
There's the operating system's own set of data, its own data structure. Just like the operating system has a data structure of all the processes.
Right.
You know, and their PC and their process control block, their PCBs. It also has a list of all of their page tables. That's why your operating system will take a lot of memory. All right. How do I get to share? Gotta go. This. And like share. And share alike. Slide, current slide. Okay, so we're back here. And we explained that there's some cache really in between. Between this arrow, along this arrow, there's really some cache, and that's what we learned in computer architecture. Okay, so I guess this is just the same thing. Associative memory parallel search. Right. This page search, you notice all these arrows here, that means that it's parallel search. We're not searching one by one, we're searching all of them at once. P is an associative register. Get frame number out, otherwise get frame number from the page table in memory, right? These are cache or registers for everyone, either way. Okay, now let's talk about effective access time, which we also talked about in computer architecture. Associative lookup is epsilon time. In other words, to look up something is epsilon, and the hit ratio is alpha. What does it mean, the hit ratio of alpha? For example, the hit ratio could be alpha is 80%, which means 80% of the time we get our page, we get our page number translated to a frame number by the TLB, and we can go straight this way, and we don't have to go to a memory lookup to get it. Okay. And 20% of the time we have to go to memory. And what is our epsilon equals 20 nanoseconds? That means the actual time, but this is the associative lookup. This is the lookup in this table, So that takes 20 nanoseconds. And it takes 100 nanoseconds for memory access. Okay. So the effective access time, we could ignore the time to copy, or we are going to, in this case, ignore the time to copy from the page table to the TLB and then reload the TLB. In other words, another way of saying it is that, yeah, we're ignoring that time. In other words, all we're worried about is the actual one-time lookup. So what is the effective access rate? So let's look at it here. It's 80% of the time it's 100. Why 100? Because 80% of the time we go here and we just go directly to the physical memory, and that's 100. Going to the physical memory takes 100 nanoseconds. So 80% of the time it's 100, but it's also plus 20 point two, this is 100 nanoseconds. No, and 20% of the time, sorry, and 20% of the time, it's two memory lookups, yeah?
Why is it two?
Why is it two? Because 80% of the time it's one memory lookup, and 20% because we have a miss. We have a miss, we didn't get to go to the TLB, we had to go look it up in the memory, and then when we got looked up in the memory, then we went to the actual memory. Right, 20% of the time, we went the long route. We went down here and then went to memory.
Oh.
80% of the time, we went here, short route. So that's what this is saying here. 80% of the time it's 100, 20% of the time it's 200, because we gotta look up in the page table and then also look up in the actual memory that we want. And then plus 20 nanoseconds. What's the plus 20 nanoseconds? Because in any case, we always do at least one lookup here. Either we find it or we don't find it. If we don't find it, then we'll go here. But if we do find it, but either way, we have to look. And that's represented by the 20 nanoseconds. Now,
Not 20 times.
now really, if you think about it correctly, it should be that there's two other calculations we have to add in. Which is if we had a miss, it's not just 20 and then 100 and 100. It's 20, but then 100, and then the time it takes to copy back into here, which is not given to us. And then another read of the TLB, that's the way you do it. You always read from the TLB, so you have to copy it back, and then it should really be plus 20 plus 0.2 times 20. Now, whenever there's a miss, there's an extra 20. But that's a small amount, so they're ignoring it in this slide. I'm just pointing out, they said they were ignoring it. I mean, actually, I changed this slide. I totally changed the slide. The original slide was all screwy and didn't say that they ignored it, and it just didn't make any sense. But they are ignoring it. And so this is the correct answer, yeah? 80 plus 40 plus 20.
Is it a small amount if we miss simply because it like physically is a small amount of time, or just because it happens so infrequently?
Well, it's 4 nanoseconds. I mean, if 22 times 2 is 4, yeah. It's 20% of the time. We have to do an extra TLB lookup. Now, TLB lookup takes up only 20 nanoseconds, so it's 20 times 20. It's 20% of 20. What's 20% of 20? 4. So it's 4 nanoseconds. So the correct answer should really be 144.
That's like.
But that's also not quite right, because there's some time to copy from the memory into the TLB in the first place. So that maybe is, let's say, another 4. So it could be 148, but it's not given to us. That information is not given to us. If I would ask this question and I wouldn't say we're ignoring the time to copy into the TLB, then the correct answer would be 144. Because we'd have to say at least 144. But again, it's a small number. 4 is a small number when we're talking about hundreds of nanoseconds. So 4 is, remember, when we're doing physical things, it's katan alim. Okay, consider a realistic, now here it says, it's funny, you thought that was realistic. Consider a more realistic hit rate of 99%. We really want to have a situation where we have hits all the time, because we don't want to go to memory twice. That would totally ruin all the benefits of having a page table if we had to go all the time twice. So if it's 99, then and a TLB is 20, then by the way, then our 4 changes to what? Even 0.2. It changed to 0.2, so it's really small. So then it becomes reasonable to ignore it, you see? If our hit rate is very high, which it should be usually, then we really could ignore that thing. So in any case, if our hit rate is 99, and then am I right when I said? I think so, yeah. Anyway, 20. So what would it be? It would be 99 times 100 plus 0.01 times 200 plus the 20 that we can't avoid. So that would give us 121. So you see, it really is important to have a high hit rate, because that's better than that. Memory protection. Yeah, in our page, I'll jump to the picture first, then I'll go back. In our page table, we're gonna have a bit, we're gonna, in addition to say, see, up till now, we didn't really say what was in this page table, which had a picture, which said it basically, what does it have? The P tells you it has the F, it just has the F. The index is just the F. So now we're saying like this, actually, let's make it a little bit better. In addition to the F, here's the F, 2, 3, 4, 7, that's the F. That's the frame number. Of course, the number would really be a lot more digits than just one digit, and it wouldn't be in decimal, it'd be in binary. it would be a lot longer, but we're also gonna add one more bit in binary, which is called a valid bit. And this is very important because we'll use this fact that there is a valid bit to save space later on. But for now, let's understand what the valid bit means. Valid bit means that, for example, here, he is not allocated, he's only allocated frame numbers 0 through 5. Another, if he has a page 0 through 5, he'll go and get it. If he over here in his program says, I decided to jump to page 1000. Well, this page table is too small, but imagine that the page table had a row 1000, or in this case, he wants, I want to jump to page 7. So he'll come here and he'll see 0. And he'll say, oh, I'll go to page 0 over here. Look, that's page 0. It's available. Go to page 0. Ah, but it's not really been allocated to me. Because remember, these page tables are memories. So there's always going to be values in them. You can't have like no value. Worst case, it's 0, but it's still going to be a value there. So if he tries to go to a page that's not his, we have to tell him that it's invalid. Because the page table is a theoretically large, it's theoretically maps all the pages, because maybe he does have page 7. And you have to use the index to get to it, so if we decide to give him page 7, we need to have a page table capable of having that. So it ends up gonna be that if our page table is not like this one, which only has 8 rows, if our page table has 10,000 rows, it's gonna be, most of them are gonna be invalid. Most of them are gonna be invalid because it's probably not been allocated the entire memory of the computer. Probably not even half the memory. He's given a tiny bit of the computer's memory. So most of these pages will be invalid. And now we're really saying it's a pity, isn't it? That we have this large page table and most of it's invalid. Right. Yeah, okay, so that's what we have this valid bit. And what does it say here? It says, basically it just says that this also gives protection, because like this 0 here is not just that it's not his, it's somebody else's. And so it's going to prevent me from getting, and that was one of the goals of the operating system, is to prevent you from going to places that you couldn't go, that you're not allowed to go. And how did we do it before? If you remember, we did it before with what?
The base.
The base register and the limit register. So now instead of that, we're just going to use this valid bit. We don't need it, right? Okay, we could still have that, but we don't need that. Wait, so where were we? Okay, so memory protection implemented by associating protection bit with each frame to indicate if, you can also say, is it read only or write only? In other words, we could give a page that he's access only to read. Why would that be good? Because let's say he's sharing that page with somebody else. Then we'll maybe indicate that the page, even though he has access to it, it's only read only. Because the other person is also reading it. Maybe why? Because it's a shared library. Let's say it's a library for the cout function, which is a shared library. We don't want that in the memory millions of times because millions of programs running. We want it once in memory. So everybody will share it, but they don't need to write to it. It's just code to run. So you just read it. So we'll have a bit that indicates that it's read only. Can also add more bits to indicate page execution only. If the page is executable. Okay. Valid, invalid, I explained. Indicates the page is not the process's logical address space. And he's not allowed to go there. Or use page table length register. Page table length register, PT. So that's also a method. We don't have to have an invalid bit. We could just say the length of the page table. And then the page table wouldn't have to be infinite. We could have a register, maybe, and then the page table could be finite. We could say, no, this program is allocated only from his logical page 0 to 10,000. That's all he does. Even though the theoretical page table of the maximum would be larger, we'll limit his. And he maybe is using all that 10,000 or maybe not all that 10,000. But we could also use that. And then if he tries to go beyond the 10,000, the page table length register will be hardware, will send us a hardware interrupt and tell us he's trying to do something illegal. We won't let him. Which is what it says here. Any violations in a trap to the kernel. Also, if he tries to go to an invalid page. Okay, so here they're just showing you the invalid page, they're not showing the page register. Shared pages. So shared code, one copy of read-only reentrant code shared among processes, text editors, compilers. Okay. I don't know why they're giving examples of text editors and compilers, but why would a program use it? I guess if a program is using a compiler, you may have you have two programs that are using a compiler. they could use it only one, they could only read it. Private code and data, each process keeps a separate copy of the code and data. The pages for the private code and data can appear anywhere in the logical address space. Okay. So here you see two programs, and this is just a demonstration, it's just showing you a picture of what we were saying about sharing pages. Because here's program process 1, process 2, process 3. And these are their pages. He's using editor, code from the editor. I don't like this example of editor. I prefer an example of, like I said, of the cout function or some library function. But let's say the editor, he's using the editor code lines 1, 2, and 3, and then his data. Maybe I'm running an editor. Maybe that's what it is. I'm running Notepad 3 times. There's 3 instances of Notepad running. So I have 3 instances of Notepad running, and they're each editing a different file, text 1, text 2, and data 3. So when I'm running this process, he's actually accessing the code, the code, the text segment. Remember, in architecture, we called it the text segment. The code of the program, he's accessing it, and it's in locations 3, 4, and 6. And notice it says 3, 4, and 6, and 3, 4, and 6. They're all accessing the same code. It's in memory once. But their data that they're editing is 2, 1, and 7. Now, from their perspective, they don't know anything about the page table will tell them where to go. And then in memory, I only have to have editor in once. So that's an advantage of having page tables once we've created it. Memory structures for paging can get huge using straightforward methods. I mean, here is ignoring the page table reference, the register, the, what do we call it? The PTLR, page table length register. Assuming we don't have that, then memory structures for paging can get huge in straightforward methods. For example, consider a 32-bit logical address space as on some modern computers. We talked about this. Consider a page size of 4 kilobytes. Okay, so I love questions like this. 4, because they're just math. A 4 kilobyte page. So that's 2 to the 12th, right? Because 2 to the 10th is 1 kilobyte. And
Bytes.
2 to the 10th is 1 kilobyte.
It's 2 to the 10th bytes.
Look, the number 2 to the 10 is 10,024.
Then you
Right.
multiply by 4.
Right.
And kilo. 2 to the 10 is 1 kilo. And then if it's in referring to bytes, then it's 1 kilobyte. We call it a kilobyte. We don't put an S there. Okay, 1 kilobytes. I don't. Anyway, consider a page of that size. How big would the page table be? It would have to have 1 million entries. Why? Because if the slices of pie that I'm making are 2 to the 12th, and the pi is 2 to the 13th, 2 to the 32nd, then how many slices do I have? Well, I have to divide the size of the slice, the whole pie, by the size of the slice, and then I know how many slices I have. Right? Because I can do the other, right? So it'll be, if you remember from 7th grade, if you divide powers, you subtract if the bases are the same. So that means I'll get 2 to the 20th. 2 to the 20th is a megabyte, or is a mega. And if we're talking in bytes, then it's a megabyte. Each entry is 4 bytes. But wait a second, that's how many entries we'd have in the page table. But maybe each row isn't 1 byte long. In fact, it can't be 1 byte long. Let's say it's 4 bytes long. If it's 4 bytes long, then the page table for 1 million entries would actually be 4 megabytes, not 1 megabyte. You understand why it's not 1 megabyte? 1 megabyte would assume that each entry in the page table is exactly 1 byte. But if it was exactly 1 byte, how many bits would it be? 8, right? 8 bits in a byte. But how long is the address? In order to, if the address is 32, and 32 is 4 bytes. But if I say, well, you don't need all 32. Here, let's say, what's in the page table? Wait, do I have it? Yeah. If you have a 32-bit, I really wish they had one. cleaner, we wipe off the boards at the end of every class.
Many,
The page you do, you
many.
stop sharing.
Affection.
Thank you.
How do I make it be me?
Click on the link.
Click on myself.
Click on your pic-
Okay. Okay, so
I did it.
look, you see over here, if I write over here, no, better over here.
You was up there in the.
Okay,
Okay.
but don't talk and distract me. You're gonna complicate things here. Complicated things. What did we say? We said that it's. The page, consider a page size of 2 to the 12. What does that mean? That means that if this is my address. I have my D. And my P. My D is 12, so my P is 20. Right? Now, when I do a page, when I go and I want to change my P to an F, how many bits do I need to replace it with? When I want to find the F, I got to change it to be a new one with D and F. How many bits will be here? Still 12. How many bits will be here? Still 20. Gotta be also 20. I gotta have enough full address. I gotta have 32. So my F has got to be 32. Now, what's in a page table? What's in a page table? Well, in row 0, 1, 2, etc., there are lots of Fs.
Yeah.
So what's the F? 20 bits. So it's got to be 20 bits here. 20 bits. And wait a second, we said there's also a valid bit. So it's 20 plus 1. So it's 21 bits at least. 21 bits. Now, 21 bits is a very ugly number because we don't want to have a hiding into the next row. You know, we want the rows to be in offsets of powers of 2. So so the question is like this: does 21 bits fit into 2 to the first? 2 to the first? No.
Yeah.
No, sorry. Does it fit in 2 to the, wait, what did I want to say? 8. 2 to the, how many bytes? How many bytes do you need to get 21 in there? 3. You need minimum, wait, 16, 1 byte is 8, 2 bytes is 16, 3 bytes is 24. So you need 3, but really, we're not gonna take 3. Because 3 is an ugly number also. Because we're gonna jump by 3s. We want to jump by units, by units that are powers of 2.
It's a power of two.
So therefore, no, but we don't want to jump by 3. 3 is not a power of 2. No, so we're gonna change, so this is actually gonna become, the page table is actually gonna become. What did I say, 32 bits per row? It's gonna be 32 bits, every one is 32 bits.
That's a waste of so much space.
Because we basically have to, because in order to do the indexing properly, you have to chop off, the way you do indexing is you chop off bits. And every bit you chop off is another power of 2. So you want to, so we'll chop off 2 bits and we'll go by 4s. In any case, my point is that when they wrote in this slide, let's go back to the share. Share. Slideshow from current slide. What I'm just basically doing is proving to you that they were right when they said for each row use 4 bytes long. They didn't just say that as a assumption. It has to be that way. It has to be 4 bytes long.
4 bytes.
And that means that it's going to be 4 bytes. So because of this, and every process has its own page table. Right? There's not, as I've been keep saying all the time, because I emphasize it, by the way, these are my own additions to these things, because in the book, they just mention it once and they just assume you know it. And they don't even mention it, actually. I don't know. It's not clear, but it's very important to understand that it's for each one. It's not one global one. The amount of memory used to cost a lot. That amount of memory used to cost a lot. And maybe nowadays it doesn't sound like so much, but 4 megabytes for every program, I want to run Hello World, and I'm going to have to use 4 megabytes. That sounds crazy. We don't want to allocate that contiguously. Also, another problem, that 4 megabytes, remember we said, has to be contiguous. So we don't want it to be contiguous. So because of that, we have three solutions. The two easy ones are hashed and inverted. But the first one is hierarchical, which we'll start with, which is a little bit harder.
This is so we don't have to have it continuously in memory.
This is exactly. This is gonna solve two of these problems. No, this is gonna, we're not gonna get rid of this. This is not a problem. That's just the way it is. Actually, in this one, in inverted page tables, we will get rid of this problem. Not just one. But in regular, in these two, we'll have still one for each process. But hierarchy, we're gonna see, we're gonna get rid of two things. We're gonna avoid contiguous, and we're also gonna not need to have four megabytes, even if theoretically the program uses memory anywhere on the computer. As long as not everywhere on the computer, but anywhere on the computer, we still won't need 4 megabytes. So we'll see how we do that. So let's go to it. Break the logical address space into multiple page tables. The simple technique is a 2-level page table. Okay, when we then page the page table. In other words, the page table is 4 megabytes, we said. Let's page it. What does that mean, page it? Cut it up into pages.
Oh.
Let's cut the page table up into pages and put those, and then have a page table which tells us where those pages are. That's why we call it hierarchical.
Put that page table up.
Look, here's our picture.
That too.
Look at this. So here's our original page table is these little boxes, 1 to 500, 100 to 700. These are why are these numbers not in sequence?
Because they don't need to be.
Because what are they? What are these numbers? Are they P's or
That's
F's?
the references to the larger.
Those are F's, right? Those are frames. Those are frame numbers. That's the frame number. And this, but what is this row? The row that's 1 here, what index number is it?
0.
Exactly. And assuming this is a certain size, let's say this is 8 rows, then this will be index 8, right? If this is 8 rows, this will be index 8. This will be index
16.
8 and 8 is 16. Yeah, this will be 16, and this will be 31. No, not 31. 16. 23.
Yeah.
This will be 23. In other words, the indexes are spread out now anywhere in memory, but right, anywhere in memory. And I'll tell you even worse, it doesn't have to be in this order. This one could be first and this one could be second. There's no order to them. They're anywhere. They could be anywhere in memory. Now, wait a second. I want to just point out, I just want to jump a little bit to the end to show you, because since I mentioned it now, how we're going to also save space. Because watch this. Oh, I got to stop the share again. See this. Because they won't, otherwise they'll see a tiny little picture. Stop share. Escape. Don't worry, I'm going fast enough. How do I make that big? Like that? Okay. All right. I don't know if that matters, but
No, you can already see it.
I don't know.
You can do that on your computer also.
Okay, so look back to this picture here. Back to this picture. Look at this. Let's say this is the outer page table. Let's say it's really bigger, let's say. Let's say I'm really using only 3 pages. Let's say I'm really only using 3 pages. Okay, with me?
Yeah.
First of all, you could say, wait a second, Mr. Danzig, this doesn't help, because how many of these do I have? I have how many of these? I have, if I have 4 megabytes of page tables, then I'll have 4 megabytes of these. I'll have enough of these to be the whole 4. It's taking the whole page table and chopping it up into pieces and spreading it out of memory, but it's the whole page table. And if the whole page table was 4 megabytes, then it's still 4 megabytes. So I didn't save any space.
References.
This box is is one part of the page table. This is another part, and all the parts are ultimately in memory. So I have all 4 megabytes. So I didn't save any memory. I just solved the problem of contiguity. But I want to show you now how I can also save space. How can I save space? Because let's say this one is pointing to a page, but all of these are invalid. Invalid. You know, this is valid. These are all valid, let's say, but this one is entirely invalid. And this one is entirely invalid. So you know what I'll do? In my outer page table, I'll put valid, and valid by the first 3. And by all the others, I'll put invalid. And then I don't even need to allocate that. And then if in the future, and if I would want it, let's say I really do want that last page, the highest value, the highest logical value. So there'll be a V here. And he'll be pointing to a page that really does exist. So on a theoretical level, I can reference any location in memory. I can reference any location in memory because these ones just take me to another section, and that section tells me where to go. But since I marked some of them as invalid over on this level, then I save space over here. I only have 4 pages allocated. I only have 4, 1, 2, 3, and the 4th one, but they still represent any possible location in memory. And I put the invalid over here, so I don't even have to put the invalids over here because they're not going to be existing. I can allocate them. So I save space that way.
So the operating system knows that they're invalid, so we could rewrite those areas that would hypothetically allocate them.
Yeah, if all of a sudden my program says it runs a new and says, give me a whole bunch of memory. So I could change this to valid and then find a page. And then it also makes it very easy for me to do a new in my program. If I all of a sudden need more memory, I just ask for more memory. The operating system finds me a bunch of memory over here. Actually, it's going to find me memory over here in the actual memory. It's going to find me some memory here and here and here. It's going to make a page. It's going to make a new page table that references those 3 spaces that I asked for. And then it's going to, wherever I put it, it's going to mark this as valid.
Really get how to solve the contiguity.
I solved them.
I don't get how.
Well, this has to be contiguous
Yeah,
because this I'll go through by indexing.
Yeah.
But these are not contiguous.
the ones.
Because the outer table is still contiguous,
Yeah.
but it's smaller. You're right, I didn't solve contiguity 100%.
It's
All the
the,
pages
it's
for
the
each
middle,
process.
Is-
have
yeah.
to be bigger.
aren't they still contiguous, though, inside the middle box? That's.
No, this box is a page.
Yeah.
I've divided my
It's still a
memory.
page.
I've divided my memory ahead of time into pages of 2 kilobytes or 4 kilobytes. This is a 4 kilobyte chunk, a 4 kilobyte chunk, a 4 kilobyte chunk. So the pages of, that's not called the problem of contiguity. If I have to allocate it in groups of 4 kilobytes, that's small.
So the page tables, the page tables can be multiple pages,
The page table itself can be what?
multiple pages, they can take multiple pages.
Well, I took the page table that I had in the previous picture. Wait a second. This page table that I had over here, here was my page table, and I took these first 3 boxes and made them made them 1 page. And I chopped it up.
Really, the program itself for each process is,
The program is over here.
yeah, they're split up into pages,
Exactly.
which is in each
Wait,
of those.
so I just was showing you, wait,
Small boxes in the middle box.
I just showed you a lot of information at once, but what is it?
In the middle box,
Wait, let's look at this picture again. Let's analyze this picture again. What this is saying is like this. If I want page, remember I want to change I have an address and it looks like this, P and D. And the goal of the page table is to change it to what? F and D, right? From the logical page number to the physical page number, or from the page number to the frame number. We call that a frame when we're talking about here. So how am I going to find the frame number? I'm going to go over here and I say, I want logical address 0, 0, 0, 0, 0. And then I want offset, 0, 1, 0, 0, 1, 0. I don't know. So he says, oh, well, look, your page number, your logical page number is 0, 0, 0. Go to row, which row to go to? 0. Well, that means go to this one. And then that tells me go here, and this is row 0. This is 0, 0, and here I see a 1. And now I can change the F to be a 1. If I had written here 0, 0, 1, I wanted to go to a different page. I'll still go to this same box over here. But I'll go to the next row in the page table. And it says here 17.
I can do the same box.
How do I, well, first of all, because this box is pointing to lots of rows over here. All those rows are represented by this number. Now, as this address grows, eventually it jumps into the next box. But in the beginning, well, we'll see how, I'll show you. Let's go with the slide. I'll go with the slide.
Can you split your PV to another?
Wait, let's advance with the slides and you'll see it's explained this again. Oh, I'm still sharing. I stopped sharing. Slideshow. Current, okay, so
Yeah, P1, P2, that's what I'm. Split your P into.
this is two though.
Go
Yeah, exactly. So this is the picture that you wanted. This, not, what used to be my. What used to be my F, or sorry, my P, is now got two parts, P1 and P2. But it's still, the D is still the D. The D is still the D, but the P is now got two parts. And the first part of the P tells me which row in the outer page table to go to. And like I said, if it's 0, 0, 0, 0, it's going to be the same as 0, 0, 0, 1. Why? Because I'll write 0, 0, 0, 0, 0, and 0, 0, 0, 0, 1. So I'll divide that in half. And what used to be the P is now referred to as P1 and P2. As long as P1 remains the same, then I'm still going to the same row in the outer one. Now the P2 is telling me which row in the inner page table. Now, wait a second, right, in this one. So I have a question for you now. How many, let's go back to this again. Let's go back. So if let's say this is let's say this D is 12 bits. Yeah, and we're still in a 32-bit world. 32-bit address. How many wait, and this is, so this is, how big is this? Well, it's 4 kilobytes, right? Equals 12 bits. 12 bits, you know, because it's 12 bits. This whole thing is how many bits? 20. So what's in a row here? This is going to be my F, right? Let's say this is the whole F. So we could say this is 20 bits. 20 bits plus 1. Right, for the valid bit. Like we said before. If it was like we said before, the simplest way to think about it is each one of these is 20 bits or 21 bits, 21 bits, etc. Now, but actually they're not 21 bits because they're 4 bytes. So they're 4 bytes. Now, if these are itself pages, how big are they? 4 kilobytes. So, because they're pages, just like this is a page. How many 4 bytes can I get into? How many 4 bytes can I get into 4 kilobytes? Well, it's what?
2 to 7.
2. This is 2 to the exactly. It's 2 to the 12th divided by 2 to the 2nd, so it's 2 to the 10th. 2 to the 10th what? Rows. There's 2 to the 10th rows in one of these. How many of these things are there?
Except one. In the original.
No, how many of them theoretically, if it's the maximum size, how many of them are there? If the program is using all the memory in the computer, how many of these do I need?
You need log of the number of adjustable addresses, adjustable bytes in the computer. Or do you know-
Well, I need 2. No, I need 2 to the 10th. I need 2 to.
the whole-
Each one of these rows represents 2 to the 12th. It points to 2 to the 12th. That means that each row I need 2 to the 20th of these rows, 2 to the 20th of these rows. But each one of them is 2 to the 10th in here. So I need 2 to the 10th of them. I need 2 to the 10th of these chunks. Because it's 2 to the 10th pages times 2 to the 10th rows gives me 2 to the 20th rows. Which is how many I needed. That's how many I needed. We said that before. We said that before that I needed 2 to the 20th rows. These are my favorite kind of, I like this math kind of stuff. We need 2 to the 20th rows. So that means we must have how many of these? What did I say? 2 to the 10th. So now we have to ask the question, how many rows are there here? You see what I'm saying? Well, each one of these rows refers to one of these. So how big is this, is what I'm asking. So it's 2 to the 10th, it's 2 to the 10th of these pages. So it's gotta have 2 to the 10th rows here. So that's a kilobyte. So we've gotten our page to be 1 kilo rows, not byte. 1 kilo rows, but if each row is 4 bytes, then it's 4 kilobytes.
Same size as the page.
Well, that's the question. What is the size of these rows? First of all, just understand that in the simplest way of thinking about it,
Reference to a reference. Can be small.
in the simplest way of thinking about it, then it would be 4 kilobytes. And that would certainly work. We have 4 bytes, that's certainly enough. But what if we wanted to make it smaller? Could we fit it into 2 bytes instead of 4 bytes? Well,
Why does it have to be 1 kilo rows?
what is this? What's the address of one of these things? The address of one of these things should only be 20 bits. Oh, you're saying there's 2 to the 10th of them?
Yeah.
But to find them, I need 2 to the 20th. Yeah, I'm gonna still need to find them, I'm gonna need 2 to the 20th. Because it's true that there's only 2 to the 10th, but I don't know where, that's if they were in a row, if they were in order, and I knew they started at this place and ended at that place, but they could be anywhere in a larger area. So I need more digits to differentiate them. You understand? I need 2 to the 20th still. So it's still gonna come out to be 4.
How can it still come out to be?
But anyway, what? It's still, what? How can it still come out to be 4?
Yeah, I don't understand. So
Well, what would you like it to be? You'd like it to be, you'd say, well, there's only 2 to the 10th of these, so I only need 2 to the 10th, I only need 10 bits to reference all of these.
right.
But I still need to know the absolute address of it in all of the memory. I need to know where it is in memory and not just which number it is. It's true, if I labeled them all 1, 2, 0, 1, 2, 3, I would only need 2 to the 10th of them. But they still could be anywhere in memory. And I need to know where they are. Now, it's true that I know that the last 12 bits I can ignore of the address. Because they're always going to start with, they're always going to be 0. In other words, memory, if you think about it, the first page of memory is from 0 to
40,000. 40.
no, to 2 to the 12th minus 1. 2 to the 12th minus 1. But that means it's from the next one is going to be a 2 to the 12th. Well, this one is going to be, the address of this one is going to be 32 zeros, right? What's the address of 2 to the 12th? It's going to be 12. It's going to be 12 zeros with a 1 here and then also zeros here. Every time I jump by a page, these are going to be zeros. So that's why I didn't need the full address of the page. That's why I could just say, well, I only need 20 bits. I don't need 32 bits because I can always assume that the last 10 bits are 0. Last 12 bits are 0. But I can't do that with these pages, I don't think, because that would assume that I knew that where they were in order, and I don't know where they are. They could be anywhere. Agree? But anyway, the point is we proved that the outer page is 4 kilobytes. Now, to say that we need 4 kilobytes of contiguous memory, well, how big is our is our page size. It's smaller, it's 2 to the 12th, which is which is, no, it's 4 kilobytes. What is, wait, 2 to the 12th is what? Our page size is D, 12 bits. How big is that?
That's 4
That's 4 kilo.
kilobits.
So it actually works out beautifully.
Kilobits.
Kilobytes, not kilobytes. 12 bits is 4 kilobytes. So actually it works out that by dividing it in the way that I just proposed, which was 12 and 10 and 10,
12 bits isn't 4 bits. 12 bytes.
12 bits represents,
Yeah.
no, each page has, it's the address space is 12 bits. A 12-bit address space references 4 kilobytes of memory, right? This is very important to differentiate. A 12-bit address space references, each byte has an address, not each bit has an address. So each of those bits represents a whole byte. So if I have 10 to the 12 bits, I have reference to 4 kilobytes, which means that if I divide this by 12 and 10 and 10, then I can actually fit the outer page into one page and everything is beautiful. If I would have done it differently, if I would have made the pages smaller by like 2 to the 10th only, then I would have not, then I would have had to chop up even the outer page, or I would have said, no, we'll just leave it as a contiguous. And that's why some operating systems have multiple page sizes. They have for the hoi polloi, they have the small pages, but for some programs, like the ones like the operating system itself, they can give larger pages, and then they can fit the outer page in. But assuming that we want all the pages to be the same size, then this scheme will work with this division. But good luck with the 64-bit. Good luck with the 64-bit address.
Well, we said that 1 kilo of rows, does each one really need to be sorry. What did we say?
I think it
10
does.
one? Because we're not referencing the bytes, now we're addressing the pages.
Wait a second, I want to share. Okay, what'd you say? We're addressing?
It just feels like, I just feel like the outer page table could be shorter because we're not addressing each byte, we're addressing the other pages.
Agreed. In other words, here, all I need to know is the page. Well, what would I write here? Let's say I would write just 10 bits here, but then what do I write in the rest of the bits? How do I know where this guy is? I still need to know. I showed you I could fill in the zeros, but can I fill in the zeros to find this guy? In other words, how can I know where he is? Let's say I write over here 0. Where is this guy? Is he necessarily in the first place? No, because there could be 2 people that have 0 over here in their outer page.
So what do we gain by having an outer table?
We gain 2 things. First of all, we don't have to look for contiguous space of 4 megabytes for our page table. Secondly, we can mark some of the rows in this outer page table as invalid, and then that whole area that would have been referenced by another page in our page table is marked as invalid. And then we don't have to allocate it. So
Get down,
so here I did a different example with 10 and 8 and 14. We don't need to go through this, but leave it as, I mean, there'll probably be a question like this on the exam, so here's another target for you to look at and see if I did this right. And in other words, we just now did the whole thing, but what did I write? I'll just say what I said here. Logical address is 32 bits with a 1K. So then the page number consists of 32 bits, right? And the page offset is 10 bits. Okay. Before we had 20 bits instead of 22, and we had 12 over here. This gives 2 to the 22 rows in the page table, if we just had a 1 level. Each row being 4 bytes long, big enough to hold the address of the page. The size of the page is now 2 to the 24th bytes. Because it had 2 to the 24 rows, but that's measuring in rows. We have to multiply it by 4, so we have to put it into bytes, and that'll be 2 to the 24th bytes, which is another way of saying 16 megabytes. That's very big. You see, well, basically what happened is we made the pages smaller. Which, by the way, helped us to get rid of internal or external fragmentation.
Next term.
Uh,
Actually, internal.
Internal fragmentation, exactly. It helps get rid of internal. In paging, we never have external fragmentation at all. It gets rid of internal fragmentation. So we made them smaller, but at a cost. And the cost was that now our page table, instead of being 4 megabytes, is 16 megabytes. It's much bigger. Since the above mentioned page table is paged, we require how many pages? 2 to the 24th divided by 2 to the 10th, because that's the size of the pages. So we're gonna have 2 to the 14th, meaning the outer page table needs to have 2 to the 14th rows. Its size will be 2 to the 16th bytes. Why did I say, again, adding 2, again, it's 4. And is addressed by 14 bits. Why is it addressed by 14 bits? See, that's I think my mistake here. The outer page table, oh, it is addressed, now to get to it. I'm not sure what I meant there.
It would need to be adjusted by 14 because of 14 rows. To get to 14 rows, you need.
No, but no, what's the address of the outer page? The outer page table itself, okay, no, that has a 32-bit address. But,
We're saying we only need 14 bits of that.
okay. An 8-bit page offset. Oh. An 8-bit page offset. Now I'm saying, all right, whatever, I'm getting to a very complicated thing here, which is that
So within the page.
the offset within the page could only be 8 bits, since each row of the inner page contains 4 bytes, and there are 2 to the 10th divided by. There's 2 to the 8th rows, so inside I can add zeros basically, is what I'm saying. There's only 2 to the 8th rows, so I only need an 8-bit offset.
This is the outer page, yeah.
We don't need more than 8 bits to reference every row in the inner table. We will access the inner table by jumps of 4 and simply append 2 zeros to every 8-bit address we're given.
Oh, so we can't. I thought we said before.
Now here we can, once we're in a page, once we found the page,
Oh,
we can jump around in it.
so how many bits do you need in the outer page?
So that's the logical addresses as follows: 8, 14, and 10. In other words. Whatever, I'm just pointing out that when you change the page size, it's not like this is always divided in half or something. You have to figure out how it's divided.
2 to the 14 rows containing the addresses of the pages, which are divided into 2 to the 8. The addressable parts, pages, subpages.
All right, now I did an example of 64 bits. Which is harder to think about, but I'm gonna skip that. And this is just like how I calculate, yeah, 46 bits, 7 bits, whatever.
So do we save space then? We just,
Well, we have to figure out what to do with the 64-bit architecture. You guys all have 64-bit computers. You're gonna have to have a page table that handles it, so you gotta think about how it works. Anyway, it's just more, it's all the same thing, but okay. Now what about a 3-level paging scheme? Which is like this. Let's say we have the offset of 12 and the inner page is 10, but the outer page is 42 because it's 64 bits, right? 12 and 20 and 42 is 54, 64. Those are 64 bits. If we have the inner page is 12, which is 4 kilobytes, and the offset, each page is 4 kilobytes, then we're gonna have an outer page, which is even with 2 levels, it's gonna be huge. It's gonna be 2 to the 42 times 4 probably, or maybe even more, times 8. Well, we might need 8 bits. We can't, how many, in a 64, what is 64 bits? Divide 64 by 8, and you get 8. A 64-bit architecture has an 8-byte address. So we need, each row could maybe have 8 bytes in it. We don't know. We have to think about it, we have to calculate it. But let's say not more than 8 bytes. Because that's an address. A normal address, if we would just not think about any savings of space, the normal address is gonna be 8 bytes long. So we're gonna need 42, 2 to the 42 rows times each row being 8 bytes long. That's gonna be 3, that's gonna be 2 to the 45th. Which is not megabytes, terabytes, gonna be, it's gonna be 32 terabytes. It's very huge, just for a page table, it's impossible out there. We basically wanna keep making higher, we wanna keep dividing like this. Until we get our outer page table to be a manageable size. And in fact, sometimes we ask a question like that in the exam, which is, how many levels do you have to do in order to get that the outer page table will be what size? Will be the size of one page. You see what I'm saying? That the outer page table will reduce to 2 to the 12. Which is the size of the page. How many would you have to do? It's just a question.
For log 12.
Anyway,
That's good.
what?
Is that like log 12?
I don't know, you guys are probably better at math than I am. I just have to work it out with paper and pencil.
We'll have to do that.
But in that, you're asking how many times do you have to,
Well, it depends on a lot of parameters, depends, in other words, first of all, just from this, I calculated that this is 10. How did I calculate that's 10?
right?
How did I calculate that the inner page is 10? If the offset is 12, how did I get this 10?
Because we said that the size of each page within the first page table can hold 2 to the 10 addresses.
Well, if it's 2 to the 12, let's think about this. If the page table itself is 2 to the 10, it's 2 to the 12, that means, and how long is an address? How long is a row? How long is a row? 64 bits, so that's 8, that's 8 bytes,
So
or 2 to the 3. 2 to the 3. So if this is 2 to the, if the page is 2 to the 12th, and the row is 2 to the 3. Right, 8 is 3, it's 2 to the 3, correct me if I'm wrong,
yeah,
so that means 12 minus 3 is 9. Right,
but
that means that there are. That means that each page can hold references to 512 other pages. Right? But each row is 3. So if I.
No, it's 8 bytes. Oh, okay, yeah.
You with me, guys?
So the first page, like table number 1.
I'm thinking it is.
It is a bit confusing. This is, yeah, look, if. It is a bit confusing. I mean, it's very confusing. That's the offset, yeah? If of 2 to the 12th. That means.
There are 2 to the 12 bytes in the.
That means I could either put a 0 here, 1, 2, or 3. That means if I got a page number, this is all, if it would be a 1 level, this would be 52 bits. And I would give this long address. And then this would be the P, and I would change it to an F. Right? And I would have 2 to the 12th. That'll be my offset, this is my D. So I've already chopped off 12 bits and I only have 52 bits. I'll give an address now of 52 bits. Now in a page, I have to store essentially in here, in one of these, I have this page here, which is 2 to the 12th. And what do I want in there? Ultimately, at the end, there's the first level here. He's got to point to one of these pages. So how many bits do I need to point to one of them?
4.
52. 52 bits.
552. To get to 2 to the 12,
Because each one of those, because each one of the pages is 52 bits and then 000 at the beginning of it.
Okay.
Right? Each page in the memory, I've taken all of the memory and I've divided up from the beginning. The first one is all zeros. The second one is, it looks like this. Second one is all zeros. At the end, it's got also all zeros, 12 zeros. But then a 1 here. And the next one is all zeros and then a 1 0 here. And then, but all of them have one thing in common. They have 12 zeros at the beginning of each page.
Right.
Right? The beginning of each page has 12 zeros because the D is 12.
Right.
So the next one is gonna be 1, 2, 3. When I get to the number, what is it?
To the-
4,000 and something, I'll get a little bit more.
13, yeah.
2 to, right?
When you get to do the 13, yeah.
When I get to 2 to the 13th, I'll go to the next page. And this will jump over here. This number will pop up and then it'll be back to 0 again. So I don't, in the pages that I'm creating to reference it, I don't need to write all 64 bits. I just need to write 52 bits. So a row, when I'm changing my, let's say I'm changing my P to an F, I just need 52 to 52. So a row here will be 52 bits. But what is 52 bits? 8 bytes. It's 8 bytes in the end anyway, because it's close to 64. So it's 8 bytes. So that means a row is 8 bytes. If we talk about bytes, it's 8 bytes again. So it actually didn't save us anything, but it actually does save us because now we have room is 52. We can add our valid bit and it becomes 53. If it had been a full byte of 64, then we wouldn't have been able to fit another bit for the valid. We have to go up to 16-bit bytes. So it's very good that it's less. So it's 52, 8 bytes. How many rows of 8 bytes can we get in here? Well, no, because this whole thing is 2 to the 12th.
2 12 rows.
It's no, but the whole size of it is 2 to the 12th. It can't have 2 to the 12th rows. It can have 2 to the 9th
Where
rows.
do we get the whole size?
Because it's a page.
Because
Because our offset is 12.
And this is 2 to the.
This is a page. This itself is a page. We're dividing our page table into what? Pages. Well, our pages have been defined as 12. So this has 8 bytes per row.
No, but it's still 2 to
And
the
it's
12. 2 to the 12.
The whole size of it is 2 to the 12. So I take 2 to the 12. How many rows can I get in there? 2 to the 9th.
I thought it was 2 to the 12 rows, that's why we have the offset is 12 bits to map to 2 to the 12.
No. 2 to the 12th is how many individual bytes are in a page. But if I'm using up 8 of those individual bytes per row, then I've got to divide 2 to the 12th by 8. Well, so 2 to the 12th, 2 to the 12th divided by 8 equals 2 to the 12th divided by 2 to the 3rd equals 2 to the 9th. So I have 2 to the 9th rows. Right? 2 to the 9th rows. That's how many rows. You're giving some queries.
Like,
I see.
we said that, I thought we said that the page table would be like in several pages, not just in one.
Yeah, but I'm starting at the first one. The last, I know, I'm starting at the first, at the first level next to it.
Yeah.
At this P3 in there,
Yeah, but that's,
P3 is a page.
has to be a single page, you can't split it up into several pages.
No,
That's
it's a
the
single page.
That's why
So then how does that solve anything with contiguity? We still have to have a contiguous page in memory.
Yeah.
For each table.
I agree with them.
No, the pages are always contiguous. Pages are small though.
So how do we? But if.
We don't have to have large.
Because only the most outer page index table, only that one has to be contiguous.
No, these are all themselves, within themselves contiguous.
Yeah, it has to be contiguous.
How do we solve contiguity?
No, the problem is that we're referencing,
No.
if we wanna reference like 100 billion pages, then we need a contiguous table.
If you had a
what
file
we're
of,
solving.
if you had a file of, I'm basically taking your file, your program, and chopping it up into pieces of page sizes. It's true that each page size has to be contiguous. But your program isn't contiguous.
So we're shrinking the page table.
Yeah.
No, we're chopping up the page table.
But we're not shrinking it because each one stuff takes up one page, it can't take up several pages. Each page, each inner page table has to take up one page.
Yes, That's okay.
We're not chopping it up, we're just.
No, it used to be more than one page, it used to be
Yeah.
a lot more than one page.
I gotta go, I gotta
We're not
continue.
chopping something.
Enough, you guys have to work on this on your own, it's very confusing, and if you don't work on your own, you won't get it. And even if I show it to you, you won't get it, so there's no point. Let's go to the
Is there a
next.
standard for how many page?
Let's go to the next
how many
topic,
pages we have?
let's go to the next topic, hash page tables. What, is there a standard number? No. The virtual, so here, common in address spaces that are larger than 32 bits. We're not gonna do this, for 64 bits, we're gonna use it as hash table. The virtual page number is hashed into a page table. What is a hashing function? Hashing function is where you put in a number and you get out a number, like a black box, except that sometimes two different numbers will produce the same output number. As I put in 64, or I put in 74, and either way I'll get out 12. I put in, but sometimes I put in 64 and 65 and I'll get two different numbers. It's just rules, it's some kind of program, maybe multiplying it by a prime number and then dividing it, who knows, it's some kind of mathematical computation that I put in numbers and I get out numbers, but I get out the same number sometimes for two different numbers that go in. Each element contains the virtual page number, the value map page number frame, and a pointer to the next element. Let's see a picture. Basically, it's like this. I take my P and I put it into a hash function. It produces to me a number, and that number would normally have been my F directly, and that would be where I go. But since two different P's can produce the same number, this can't be my F. Instead, this will be a pointer to a list of Fs, to a list of Fs, to a list of frames that are possibly the right one for you.
How would I use,
And then what I'll do is like this. I'll say, if I put in P, let's say I put in 74, and I got this row, it told me go to this row. And the first number I see here is not 74. So I skip it, and it has a pointer to the next one, it's a linked list. And eventually I say, oh, there's 74, that's how I got here, was 74. Now, I'll look at this R that's there, and that'll be where the actual frame is. That's really the F. I don't know why they call it an R, but they call it an R because they want to differentiate from the S. But this is the F that I'm looking for, and that'll tell me. So actually, how big will this entry be? Well, assuming the pages are 2 to the 12th, then these will be this is 2 to the 12th, this is 2 to the 20th if it's a 32-bit thing. So this is 2 to the 12th, this is 2 to the 20th. So this is 2 to the 20th, and this is 2 to the 20th. So notice this is 20, sorry, not 2 to the 20th. This is 20 bits and 20 bits, 40 bits. Plus a pointer to the next one. The pointer will probably be a bunch of bits too. So these will be like, let's say, I mean, the pointer will probably be 4 bytes. So 40, and it'll be 40 plus 32, 72 bits. These will each one will be 72 bits.
that's like a linked list.
And that's a linked list.
Tables.
And so therefore, if I have a hashing function, imagine a very stupid hashing function that only produces 0 or 1. It could be you could have a hash function either produce 0 or 1. No matter what number you give it, either 0 or 1. So then I'll have 2 rows here, and then I'll have very long linked lists. Or I could have a hashing function which produces me 1,000 numbers. Then I'll have a longer thing here, but shorter lists, because the things will be spread out more. So I can determine the size of my hash table however I want, depending on my hash function. I can make it bigger or smaller. That's hashed. Inverted page tables. Yeah, I just want to finish. Inverted page tables, because I don't think, inverted page tables are also a clever idea, where what we say is they have one page table for the whole computer. One page table for the whole computer. One for the whole computer. So therefore, this is the whole size of the, so therefore this will have to be contiguous in memory. And this will be, but we'll only have one of them, so it's okay. We'll have one, that's how big will it be? If it's 32 bits, it'll be big. If it's 64 bits, it'll be really big. Depends on the size of the pages. You don't know, but you don't know how big it is. It depends on the size of the pages. But if it's 32, if it's 20, it'll be 2 to the 20th bytes. No, it'll be 2 to the 20th rows times 4 bytes. So it'll be 2 to the 24th. Whatever, it'll be 4 megabytes. It won't be so big if it's a 32-bit. If it's 64-bit, it could get very large unless their pages are also large. So the CPU will first of all, there's a PD. Every time there's an address, he'll produce a P and a D, right? And we want to get the F, or we're calling it an I for some reason. But we want to change the I. Well, why are we calling it I? I'll tell you why. Because since this is every single place, this index tells me which page it is. In other words, if I go down here and I gave it a P, and he found it over here, let's say he found it on the third row. So the I is actually 3. So then that tells me if I found P, all I'm writing here is P. I'm not writing the F. I'm just writing P, but P itself is on the third row. So that means that the actual frame for P is 3. If his page was, let's say, 0. So he's looking for 0. He goes through and he finds 0, but 0 is all in the last one. Then that means page 0 is the frame way down over here in the end of memory. Depending on where he finds it. Wherever he finds it tells him where to go. And you say, wait a second, there could be 2 programs that have 0. Totally reasonable. So how do you find it? So you also put in the page table, you actually have to make it bigger. You have to put in also the process ID number. So when we search, we'll have to, and also the search will have to be, either it takes a lot of hardware to do this. If we make a page table like this and we do a parallel search, then we'd have to have hardware that accesses every single row, which would be very expensive. So if we don't do hardware, we'll have to search, and that'll be slow. So it's actually, from my understanding, an idiotic solution. Like, it's theoretically nice, but it doesn't really make sense, because the downfalls are either you have to have hardware that is very expensive and capable of searching all this simultaneously, or you have to do a step-by-step search, because it could be anywhere what you're looking for. Because it could be your page 0 is the end of the row. You don't know where it is. And then you'll get your 0, and that number will be very large, and it'll take you to go here. So that's inverted. We're done. I don't think I want to stop here for the day. We'll do it for the day. What? The whole day. 45 minutes afterwards. I have something to do. That's the thing.
Okay, so we're gonna stop here for the day.
I'll stop here for the day. We finished.
Yes.
What's that?
But different computer science.
Yeah, we have that now.
That's like in an hour.
Yeah.
We're gonna have next week. We don't have class.
Yeah.
At all? Yeah, let's do.
Yeah, next week is break it up.
Oh, yeah, you got it.
Also,
Next week is completely free.
Wow.
We have Zoom on Thursday,
Yeah.
but I'm gonna cancel it, I think. As far as the lab.
Sure.
The lab. We have another class on Thursday?
No.
No, it's not the lab. I'm gonna cancel the lab.
Sorry, which one did we talk about last night? Or not last night?
It's posted.
It's posted?
Posted on YouTube. The lab from Thursday. I posted.
I gotta read
know.
It's a good behind on so much.
Yeah, after.
It's a lot of.
I know.
What? The truth is.
Yeah.
Are you gonna go home?
You should read ahead.
It's
hard to get behind. Right.
Yeah, I gotta.
Sure.
I'm only taking 3 courses this semester, but I gotta catch up on all.
So.
Let's see where we are. We're okay as far as time. That's why I don't mind missing.
Did you by any chance have a Topus FS for the module class?
And send me an email.
Okay, thanks.
English. So what are you?
I don't know, I think I'll come back to the board.
Yeah, I guess. Once the computer science works together.
Yeah, I'm down.
Let's do it.
Good idea.
I just think that it's Saturday. I can get something to eat and drink.
Should be able.
Huh?
Should be able.
I should do that. Thank you, Professor.
Oh, I forgot to
See you. See you like in 2 weeks, I guess.